A few queries away, the day Slack's database nearly crashed. So in this video, we will be discussing how a few user queries almost crashed one of the databases used by the Slack. We will be discussing in the engineering blog how they identified the cause that triggered this issue, what they did to mitigate the issue, and what new features they implemented such that this issue does not happen again. So let's begin. Let's first go over the incident that first highlighted the issue that was in the backend. The issue began on October 12, 2022, when Slack's team faced an unexpected surge in the failed databases query. This prompted an immediate action as the team huddled to address the situation. So after digging in, they found out the root cause, which was causing the issue. That was a long-running async job. So it was discovered that a long-running asynchronous job was purging a large amount of database records, leading to an overload on the database cluster. So what was basically happening is that since it was deleting a lot of the rows or data from the table, there were a lot of writes happening, and due to this, the database slowed down, and as it kept on increasing as the writes increased and increased, it led to database crashing. Immediate mitigation. To mitigate the issue on the hand, the job queue team installed a shim. Since the writes were happening due to a async task, so a queue was involved. So the job queue team installed a shim. So a shim only allows the current or the existing tasks in the queue to be executed, but it does not allow new tasks to enter the queue. So this was done because since there were a lot of writes happening, and the number of writes were the reason the database was failing. So by preventing new jobs or new tasks to be and to enter the queue, they decreased the number of writes, and this in turn reduced the load on the database. However, this problem recurred again. On the very next day, a similar issue occurred, but with some more severity. That this time once again took the team once again took action to maintain the cluster's functionality. They once again installed a shim. So basically, they wanted to decrease the number of writes, and this happened again. But but this problem reoccurring once again showed that this was not a one-off issue, and there was an edge case, or there was something going on wrong on the back end that needed to be fixed. So before we understand what triggered this issue on the back end, we first need to understand Slack's data storage strategy, like how Slack stores its data, because that was the root cause because of which this database failure was happening. Slack uses relational databases to store the data, and more specifically MySQL. Since Slack has hundreds and millions of users, storing all of this data into a single MySQL database or a MySQL server is not possible. It would slow down the reads and the writes. There will be a lot of memory out of memory conditions that will uh, overload the database. So instead, they use a MySQL cluster. Now, a cluster of databases is very difficult. It is very difficult to manage a cluster of databases manually, and so that is why they use something called a Vitess. So Vitess was originally created by YouTube for managing MySQL clusters. So it uses Vitess for managing its MySQL cluster. So what Vitess does, it helps in organizing tables into key spaces. So in Vitess, each key space is composed of a shard, which is like a slice of the key space storing key ranges of key space heights. So if I have to explain it in simple terms, they use sharding. So what is sharding? So let's understand the concept of sharding through this diagram. So here we can see we have three shards. Shard 1 stores user ID from 0 to 100. Shard 2 stores the user ID from 101 to 200. And shard 3 stores the user ID from 201 to 300. So what we do in sharding is that we take a range of data and divide it, and each shard gets a division. So how we do the partition depends on what kind of algorithm we are using. Optimally, we want each shard to have the equal amount of data, and the reason for this is because if one shard has a lot of data and the other shard has less data, then the response time will be uneven. So optimally, each shard should have the same data, and this is what Vitess does. So for each key space, there are shards of MySQL instances that stores a range of data. So, along with using sharding to decrease the response time and to decrease the read time or decreasing the load on the databases, uh, Slack also uses master-slave architecture for increasing fault tolerance and also for increasing the read efficiency of the database. So, Slack ensures high database throughput and fault tolerance by using replicas for each shard. So, as you had seen in the previous diagram, that how each shard contained a range of data. So like shard 1 contained the IDs of the user data from 0 to 100. So now think that each shard has also multiple MySQL databases or MySQL instances uh, that are in sync with that shard. So primary tables handle data modifying queries while replicas are responsible for select queries. So when you update a user, let's say user's name, so that only goes to the primary table. Then that data is replicated to those replica databases. So once they are in sync, so when a user wants to read its data, so instead of hitting the primary database, you can hit the replicas. So the main advantage of using this is first of all fault tolerance. So what happens when the primary database goes down? Well, we can just take one of the replica which was in sync and make it the primary database. That is one of the advantage. Another advantage is that now the primary database is not a single database that is responsible for read. We can just distribute the read request among the replica databases. We can use any load balancer algorithm that we want. So we not only have we increased the fault tolerance, that is there is now no single point of failure, but also improved the read efficiency. So here it is, when the data is updated in the primary database, the result is then replicated to the secondary database. So as you know that we have to replicate this data over a network. So there will always be some lag. So let's say you updated your user ID. So it might take 5 minutes or 10 minutes for the replica database to get the updated data. So this is what we call as eventual consistency. So the database, as soon as you make update, is not consistent. Means we have stale data, but sooner or later, hopefully sooner, the database gets the updated value, and when you make a read request, you get the correct data. So as per the Slack team, so if the database lag is more than an hour, then the replica has to be replaced. So basically, they are saying that okay, it has been an hour, we don't have the uh, actual data, we have a stale data, and replication is not taking place. There is an issue. Let's kill this replica or like take down this replica, host another one, and then we can just get the updated data. So we will discuss it here. Now that we understand how Slack stores its data, like what is replicas, what is sharding, what is Vitess, we will understand what triggered the issue. Well, it was bulk user removal. The trigger of this incident was tracked back to a customer removing a large number of users from the workspace. It was a rare operation because usually what happens is that when somebody leaves the company or when there's a firing, a few employees are removed from the workspace. But in this case, a lot of users were fired from the workspace at once. So it was a rare operation that led to the spike in the database load. The action triggered the forgot user job, leading to a surge in database query. So basically what happens is that each user is subscribed to a thread, each user is subscribed to a channel, etc. So when a user is removed from the workspace, you want that user to quote unquote forget about all these threads. So you want to delete all of these threads and data from the user or remove it. So each user removal involved unsubscribing from various channels and threads, multiplying the database load significantly. So suppose like you are removing 1,000 users and each user is subscribed to like 50 channels. So 1,000 into 50. So that many requests or that many queries you have to perform. So as the number of users increases and increases, this increases the database load because you are making a lot of writes, basically deletes. So you are making a lot of updates, and this is what caused the issue. So now that we know what was the trigger that caused the issue, let's look at how it affected the shards, the database on the backend. So I hope you remember that I said that it is good, that it is a good practice that the shards, that the data in the shard should be equally distributed, because we don't want one shard to have a lot of data and one shard less data, as it can cause imbalance, right? Because one database instance will be having huge load while the other one will be having less load. Well, looks like something happened here. A significant challenge arose in one of Slack's database shard, handling 6% of user subscription data. So for that particular user, means all the users that were being removed from the workspace, 6% of that subscriptions data was in one shard. So this shard faced an overwhelming volume of requests, leading to a series of complications. So, as there were a lot of writes, updates, and deletes happening, the shard's replica struggled to keep up with the primary, causing a replication lag. So, as the number of writes increased, the primary was not able to replicate the data, updated data, to the replica. And so, as more and more writes increased, the replication lag kept on increasing, the data kept on becoming more and more stale. So, also, it was one thing, but memory issues were another. The high write load led to an outer memory condition, causing the system to terminate the MySQL process. So there were so many writes happening that it was there. So the memory usage was so high that the system terminated the MySQL process. I hope you remember that I mentioned a failsafe, that when a replica has a lot of replication lag, that is more than 1 hour, when the data has not been updated for more than 1 hour, then the replica is taken down and in its place a new replica is put. So in response, a replica was automatically promoted to primary. Why? Because the primary database failed, and like I said, that once the primary fails, then we can put a replica in its place. However, replacement tablets provision to catch up. So the replacement, the new replicas that were provisioned, they were not able to catch up since a lot of write requests are happening, couldn't handle the load. So leading to a repeated cycle of failure and automatic replacement. So every time a primary failed, a replica took its place. A replica took too much time to catch up to the actual data to handle so much load. It failed, and then another one was provisioned, and this cycle kept on happening. So, like here, the infinite loop of failures. This situation caused an infinite loop. The primary fails, a replica is promoted, the new replacements fail to catch up, and being deprovisioned. So this kept on happening, and this caused more issues. Now that we know the cause, we know the trigger, we know how it affected the backend, the databases, the backend services. Now let's see how the Slack's engineering team solved this issue. So, first of all, addressing the infinite loop, like so, the replicas were being the primary failed, replica took its place, too much time it took to catch up to the actual data, and then it was deprovisioned. So, it was an infinite loop. So, the data stores team tackled the infinite loop of primary failures by manually provisioning large instances type of each replicas. So, the reason for using large instances is because, as you remember, that the the write requests were so many that it was causing the process to consume so much memory that that it it killed the MySQL process. So to prevent that, a system with more RAM and more processor was used. And as you had seen that it was like the automatic provisioning and deprovisioning of the replicas was causing an issue. So now the data store team was doing all of that manually to prevent that infinite loop. So by provisioning large instance type, so the failures became less and less, and by using the by manually provisioning the replicas, the infinite loop was resolved. So optimizing the forget user job. So this was the async job that was causing this issue because one user was subscribed to so many channels, threads, etc., that it caused the issue. Means there were so many writes happening that it overloaded the database. So the forget user job originally caused the high database load, underwent significant optimization. The team restructured the job to reduce its impact on database during bulk user removal process. So they optimized this function to prevent this from happening in the future. So a client's team had also contribution in resolving this issue. As a final step, the client team temporarily disabled the thread view feature in the Slack client, cutting down on read queries and easing the load on the database replicas. So as the backend team, as the data store team, by resolving this issue, the client team, so they removed all of this feature, the features that made a lot of read requests to the DB. So this reduced the load on the DB, and the DB could process or could focus on processing the writes request. Now that the issue was resolved for the time being, let's see how Slack's team, what steps did they take to prevent any such future incident from happening. So the first one was throttling mechanism implementation. A major step was the adoption of throttling mechanism. This controlled the rate of query processing, helping to manage resources and effectively and prevent query overload. So basically, what they wanted to do is that a queries or any job cannot exceed a threshold of memory or the processor usage. So this cannot, so a task cannot cause the system to crash. So the team also implemented a circuit breaker pattern. So the team also adopted the circuit breaker pattern, a crucial fail-safe mechanism. It monitors the replica health and temporarily halts queries to unstable shard, allowing the recovery and stability maintenance. So if it monitors, it's like a health check, I can say that when it monitors a shard is not able to process the queries in time, there are a lot of dead requests, and the RAM and the processor usage has shot up, that means something is wrong. So it halts any request, and then the shard can recover either by itself, or someone can look into it and then fix it. So this prevents the shard from totally failing. So this is it. So this is how Slack's data store team identified the cause. Like, so we went to the cause, then we understood how Slack's the data store team stores the data, in how they use Vitess, how they use MySQL sharding, how they have replicas for each of the shard. Then we understood what was it triggered. Like, it was an edge case, removing so many users at a time that they did not expect it. Then once the trigger was found, how did they mitigate the issue? Like, how did they solve the issue? Like, the clients, they stopped like sending the read thread request to reduce the load on the DB. How the data store team, they, they manually provision the replicas, etc. And then how they prevent, how, what steps did they take to prevent any such incident from happening again. So I hope you like this video. So if you did, please subscribe. Thank you.